my name's Aleksander Kaluza, and this is my presentation for Lab 5 for Physics 2212. To begin, the purpose of the lab was to observe a falling magnet through a conductive tube and model the magnet-tube interaction in GlowScript. Some essential physics ideas we use are Faraday's law, Newton's second law, and some application of Lenz's law. Faraday's law is displayed here on the right. And some preliminary findings through the experiment we had to do. I found that the average time for the magnet to fall through the aluminum tube was 0.968 seconds. How this presentation will look is, first I'm going to go over the experimental procedure, then go through the code, and then the essential questions we had to answer. For the experimental procedure, I used a ruler, roll of aluminum foil, and a bar magnet. Some of the measurements for the tube of aluminum foil was that the length was 30.8 centimeters, the width of the aluminum was 1 centimeter, and the inner radius of the tube was 1.2 centimeters. As I mentioned before, the average drop time was 0.968 seconds, and the chart on the right here displays the various findings. Here's a link to the code. It should also be found in the description of the video if you want to take a look. So for step 1, first things first, I put in the different measurements that I found, and then I used the moment that I found in lab 3, being 3.69 for the magnet, and I kept the mass the same. In step 2, I also used code from lab 3 for the method to calculate a magnetic field given a magnetic moment and a vector r. And then in step 3, this was a very important function for this lab, was to calculate the change in flux over change in time given a magnet and a ring. I used the formulas we learned in class and used the y position for the distance to come up with this code here for the lab. Then for steps 4, 5, and 6, the ring current, as we know, is the change in flux over change in time divided by the resistance of the ring. And then in steps 5 and 6, I used the dipole function to find the magnetic field due to the magnet in the ring. And then sine theta was found by doing the cross product of mu hat and magnetic field hat. And then to find the force, I applied an equation from class, as you can see below. And then for steps 7 and 8, the gravity force, as we know, would be mass times gravity. And I put a -1 since it would be in the negative y direction. The net force would be the gravitational force plus the magnetic force. And then to update the bar velocity, I would add on to the current bar velocity F net divided by mass times delta t. And to update the position, I would do something similar, where you do the current position plus the bar velocity times delta t. Here on the left is an image of the model as the magnet is close to the middle of the tube, and my results, the chart is on the right, and it came out to be 0.41 seconds to fall through the tube. So to interpret the simulation, the intensity of the coloring of the tube indicates the magnitude of current flowing through each ring. Which color corresponds to clockwise current and which counterclockwise? How can you know? So the red represents the clockwise current and the blue is the counterclockwise. So going back, we can see that the clockwise is on top, counterclockwise is on the bottom as the magnet falls through. A simple way of knowing this, I use just the right-hand rule that we had learned and simply visualizing the magnetic field that the magnet creates around these rings. And what happens to the dynamics in the system when you flip the magnet around, it will change the magnetic flux. So the current would be counterclockwise on top and clockwise on the bottom. So the colors would be flipped. So how does the total time in tube compare to what? Compare from computational to real life? So the computational in my case was much shorter. Some of the error I found may have been my own human error in reporting the time. Also, I could have calculated an incorrect magnetic dipole in lab 3, and also may have had some mismeasurements in terms of tube dimensions. And what does the shape of the velocity versus time plot tell us about the forces? A negative slope means that gravity is acting on the magnet. And then when the slope is 0 of the velocity versus time, we know that the forces are balancing out, slowing the velocity of the magnet. Some what if questions. If the resistivity of the conductor were reduced as close as possible to 0, this would increase the current and the magnetic force, and the magnet would fall slower. And if there were slots in the tube, this would mean there was less rings in the tube and means smaller force, which means the magnet would fall faster. Thank you.